This is lecture 8.4, which is more examples on how to use ice charts. These are just a little bit more involved and involve a couple of different things, so I wanted to kind of give you an idea of how this works. The first thing that I want you to think about is that you would be welcome to try these on your own, especially the first one. I think by now you should be comfortable with how that one works. So if you want to, feel free to stop the video before we begin. Here's the question. You can stop the video here if you want before we start, and then you can turn the video back on and check your answers. I'm going to go ahead and add a page so I have some space to write, and I'm going to go ahead and get started. So in this question, they give you the equation and they tell you that you are starting with your reactants and that it reaches equilibrium, and then they give you something that I always pay really close attention to. They give you the equilibrium concentrations of all four things. Okay, so this means that you know where this settles out at equilibrium and you can kind of go from there. So the first part of this is actually a review, mole fraction, as opposed to an equilibrium question. But remember that mole fraction equals moles of the part over total moles. So since this is moles per liter and we don't know the volume, it really doesn't matter because we can compare them as moles. So let's see what we need. They want the mole fraction of CO, so there's 0.30 moles of CO. And I need to add up the total moles, so that would be 0.20 plus 0.30 plus 0.55 plus 0.55, because there are two substances, the two products, that have 0.55 moles. And I'm just going to solve for that really quickly, and that gives me 0.1875 or 0.19. Again, this is more just review. This is like a question that started to pull in information from other places, so this is just kind of pulling in a topic from before. So now part B actually begins the equilibrium piece. Using the equilibrium concentrations, calculate the value of Kc. So I need to write my equilibrium expression for this. So from the equation, I'm going to do products over reactants. So that would be the concentration of water, which is weird because we don't usually do that, but notice that it's water vapor. And so we can talk about moles per liter of that, and times the concentration of the carbon monoxide. Neither one has coefficients, so no exponents. Divided by the reactants, carbon dioxide and hydrogen gas. Concentrations, make sure you have concentration brackets there. And again, neither one has exponents, so this is kind of what it looks like. And now we're going to substitute in what we know about equilibrium concentrations. So the H2O and the CO are both 0.55, and the carbon dioxide is 0.3, and the hydrogen is 0.2. And when I do the math, I get 5.0416, a bunch of numbers. I really only have two significant figures, so the Kc value is 5.0. Okay. So now the next thing they want is Kp in terms of Kc. So remember that your formula for this is Kp equals Kc times RT to the change in moles of gas. So I'm going to substitute in the Kc that we just found times 0.0821 times Kelvin temperature. So we're at 2000 kelvins. And all of that, not the 5, but everything else, needs to be raised to the change in moles of gas. So I come back to my equation, and I see that the products have 2 moles of gas, and the reactants have 2 moles of gas. So delta Ng will be the products minus the reactants, so 2 minus 2, which is 0. So I can say this is to the 0, which means all of this is really equal to 1, so Kp equals 5.0. And this is a fast way to do this in the multiple choices, to not even worry about setting this up, but to calculate your change in moles of gas first, because when you realize that the change in moles of gas are 0, then Kp equals Kc. All right, so I have parts A, B, and C finished. Let's go look. It says when the system is cooled from 2000 kelvins to a lower temperature, 30% of the carbon monoxide is converted back to carbon dioxide. Okay, so now they want the value of Kc at the lower temperature, which means I need to know the equilibrium concentrations at my new temperature. And this is going to shift because temperature changes the relationship of the forward and the reverse reactions. We haven't really talked about that much yet, but so we need to set up an ice chart because I need new equilibrium concentrations. So my equation, CO2 plus H2 is at equilibrium with H2O plus CO. Set up my ice chart. My initial in this case is what they gave me at my original equilibrium because that's where it's sitting when I change the temperature. So I had 0.30 moles per liter. Remember, this has to be in molarity, but that's what they gave me was molarity. 0.20 and 0.55. So even though this was at our original equilibrium conditions, we're changing the temperature, and so now these are our initial conditions. They tell me then that when it's cooled, the CO is converted back to CO2. So that means that this reaction is going to go this way so that the CO can be used up. So I'm going to do minus X and minus X for those, plus X and plus X. They all have coefficients of 1, so that makes this pretty easy. This is 0.30 plus X and 0.20 plus X. These are both 0.55 minus X. And then they want me to calculate Kc. So if I want Kc as water concentration times carbon monoxide concentration over carbon dioxide concentration times H2 concentration, that means I need to know those concentrations. And right now I don't know them because there's an X in there. All right, so I need to go back and reread my question to figure out what they told me. And they said here, 30% is converted back. Okay, so that means that the converted back part, X, is equal to 30% of what I had. So 0.30 of 0.55, or 30% of what was there. So this is a way for me to figure out what X is, right? So I do that math and I find that the 30% of 0.55 is 0.165, right? And since it's just X, that equals X. If there was a coefficient of 2X there, I would have to say that 30% of 0.55 equal 2X, and I'd have to continue to solve for X. But they have to give me a way. If I don't know K, they have to give me a way to know X. And if I don't know X, they have to give me a way, I have to know K. So these are kind of your two options, solve for X or solve for K, all right? So, so the idea would be that I have to, since I'm solving for K, I have to know X. So in this case, I can come back in and I can figure out the equilibrium line of all of this by substituting this value for X. So 0.30 plus 0.165 is 0.465. 0.20 plus 0.165 is 0.385. 0.55 minus 0.165 is 0.385. Sorry, I was mistaken. This value here is 0.20 minus or plus 0.165 is actually 0.365. Sorry, that was an error there a second ago. All right, so now I know all of these are at my new equilibrium, and these two are the same. Okay, so I can take them and substitute them into Kc. So I have to be careful, make sure I get the right things in the right place. 0.365. Sorry, start over. The CO and the H2O are these two. So 0.385 times 0.385 over the CO2, which is the 0.465, and the H2, which is the 0.365. And I solve for that, and I get 0.8733, which is 0.87 with two significant figures. I kept 3 here, but all of my givens had 2, so I have to bring it back down to 2. Okay, so then part E says in a different experiment, they mixed a half a mole of H2 and a half a mole of CO2 in a 3-liter reaction, and they're back at 2000 Kelvin. So this was my original. This you have to be really careful to pay attention to because this is not the new K, this is the original K. So use the given K, okay? Which, or actually it's not really given, but it's the one that we found in the KC or the KP found in parts B and C. Okay, so so the idea would be that this is kind of where we're headed, and we have to pay attention because this is moles in 3 liters, so they're not going to give me molarity there, and they want to know the equilibrium concentration of CO. So now I'm back to writing the equation again. I need a new page. I'm back to writing the equation again. So this will be CO2 plus H2 at equilibrium with H2O plus CO. And my 0.5 moles divided by 3 liters is a molarity of 0.17. Okay, so I'm going to go ahead and put in 0.17 for both of these. And these were at 0. They told me I didn't mention them, which means I don't have them. These will both be minus x. These will both be plus x. So this is 0.17 minus x, 0.17 minus x, x, and x. And I'm going to use my original KC, which was 5.0, equals x times x, my 2 products, over my 2 reactants, 0.17 minus x and 0.17 minus x. And I notice that this is a perfect square, so I'm going to take the square root of both sides, and I get 2.236 equals x over 0.17 minus x. When I solve for x, I'll let you do the math and make sure that you can do it. I get 0.117, which I have to round to 2 significant figures, which is 0.12. And this is x, and they want the equilibrium concentration of CO, which equals x. So this is the equilibrium concentration of carbon monoxide in that scenario. Okay, so that was that example. Let's try a new one. Again, you'd be welcome to pause the video and try it yourself, or you can just listen along and copy as we go. So let's see what happens. This one looks a little bit different. They give me a graph here, or they give me data here, and they tell me that solid carbon, so I want to really pay attention to that, and carbon dioxide are placed in a 2-liter container, and the reaction occurs. As it proceeds, the total pressure is monitored, and when we're done, there's still some C remaining. This tells me that it's at equilibrium, okay? And so, or actually it doesn't tell me that, it just tells me that if there wasn't a limiting reactant, it would not be the solid carbon, all right? So I want to then notice that here it stops changing. So this tells me that it's at equilibrium, all right? So they want the Kp for this reaction, so I'm going to go ahead and write this here. Kp equals the pressure now, remember to use partial pressures, of CO, this is my product, squared because of the coefficient of 2, over the pressure of CO2. Notice that this is a solid carbon, so leave it out of your equilibrium expression. That's really important. Okay. The next thing they want is the moles of CO2 initially placed in the container. So they don't tell me how much. They don't give me any idea of how to do this, except that they tell me that at the beginning it's only CO2, okay, because this is not a gas. So this is the only gas, which means that this pressure has to come from the pressure of the CO2, which means that I can use PivNert because they gave me a temperature and a volume and I have the pressure, so I can use that to find moles. So I'm going to add a page, oops, come here, add a page, and let's use PivNert to find moles. So now you're going to see how the year all comes together. So N equals PV over RT. The pressure of the CO2, which is what I'm looking for, is 5 atmospheres. And the volume they told me was 2 liters. and R, we're using 0.0821 here, always, because it's in atmospheres. And the temperature, they told me, was at 1160 Kelvin. Be careful to make sure that it's actually in kelvins when you do this. Okay, so now I'm going to solve for number of moles of CO2, and I get 0.105 moles of CO2. All right, so I've done A and I've done B. Part C says when it's at equilibrium, the partial pressure of CO2 is 1.63 atmospheres. So they want the partial pressure of the CO. So I used my ice chart again. So I did carbon solid plus CO2 yields 2CO. And I need my ice chart because I know the initial, and I am looking for the at equilibrium. Okay, so the carbon's a solid, so don't consider that. You need to be really careful with that. And from this chart, remember, we know that the initial pressure of the carbon dioxide was 5 atmospheres. So I'm going to put 5 atmospheres in here, and this was 0 because they started with only the carbon dioxide. So this is going to change down by x, and this is going to change up by 2x, which gives me 5 minus x and 2x as values. And I don't know K because that's what they're asking me to solve for in part B. So since I don't know K, I have to have another way to find X. Okay, so I reread my question and I see that they tell me that at equilibrium, the partial pressure of the CO2 is 1.63 atmospheres. So this is the partial pressure of the CO2 at equilibrium. So 1.63 equals 5 minus X. And so I can come in here and solve for X, and I can find that X equals 3.37. There's another way. I could have done this and taken the total pressure from here and set that equal to the total pressure, which would be 5 minus X plus 2X. But this is the faster way to do this. So once I know this, this is the pressure of the CO2 at equilibrium, and I can find the pressure of the CO, which is what they want, by substituting it in here. So the pressure of the CO equals 2x at equilibrium equals 2 times 3.37, which equals 6.74 atmospheres. Okay, so that's part I there. And then they want the Kp. So now remember we said Kp equals the pressure of the CO squared over the pressure of the CO2 at equilibrium. And I know both of these at equilibrium. I have them here. So the pressure of the CO at equilibrium is 6.74. I'm going to square it. The pressure of the CO2 is 3.37. And when I, I lied. Back up a little bit. Hang on. The pressure of the CO2 is not 3.37. The pressure of the CO2 is 1.63, which is what they gave me. Sorry. I need to make sure I'm really careful with that. So the 5 minus x, I was solving for x. X is 0.37, but the equilibrium pressure of CO2 is not x. It's 5 minus x. So I need to put the 1.63 in here. And when I solve that, I get 27.8696, a bunch of numbers. And again, I think I have 3 significant figures in this question, which will be 27.9 equals Kp. So 2 examples, both showing you how you can, not knowing K, solve for X. Hopefully this is helpful, and we'll practice some more in class. So